Great. Thanks, everyone. I'm really happy to be here today to talk to you a little bit about what we're doing at the Geospatial Innovation Facility and how some of that is leading to enhancing access to biological and environmental data through open web tools. So a little bit about the GIF. We're a UC center supporting geospatial research and activity, but we also have an applications development team where we're producing a lot of web mapping and data visualization resources. So there's been a bit of a shift in focus as a geospatial lab over the last few years from being purely driven by analysis and problem solving to really now shifting to increasingly working to help scientists consume and share information in more open and engaging ways. I think it's safe to say that the public's appetite and aptitude for spatial data is growing exponentially. Here's just an example from last week. If you clicked on the most clicked map or most clicked articles in the New York Times, it was a web map showing fan allegiance to baseball teams by zip code. So you can zoom in really closely, and based on Facebook information, they mapped out in great detail all of the baseball allegiance. Another map you may have seen recently that was quite popular making the rounds is about dialect, where a graduate student actually from NC State built an amazing application that compares dialects across the country, and you could take a short little quiz to let it map where your dialect it believes you are from. I grew up in northern New Jersey, and that map on the right is after my quiz, so worked pretty well for me. We're working on tools to try to do similar things at the GIF, and one of the ones that we've worked a lot on in the last few years is called CalAdapt, which helps people explore climate change data for the state of California. And we built this in partnership with the California Energy Commission. And I'm just going to give a quick demo of some of the things you'd find on the CalAdapt website today. So there's several tools that show things about temperature, snowpack, precipitation, sea level rise, and wildfire risk, all projected out through the end of the century. And so here's a map showing average annual temperature from 1950, and then you could use a slider bar to project that out all the way to 2099 and see how those temperatures are projected to change. You could also click on the map and generate a chart that shows you different scenarios and what might occur in those areas that you're choosing for a low and high emission scenario. And for those who want more and more detail, you could actually get into the actual scientific models and months instead of just average annuals, and then the lows and the highs. And all of this information is coming from different labs around the state. Here you'll also be able to see that you can generate a dynamic URL. So if you're changing a lot of these variables and want to share that with someone, that's all carried in that URL. And here's the information that's showing you where the data actually came from, in this case, Scripps at UC San Diego. I'll show you a couple more. This one here, instead of showing you the actual projected temperature over time, is showing you degrees of change. So in this case, we've taken the end of century temperatures and subtracted them from the historic range to give you a number of degrees that are projected to change. And you could see that it varies throughout the state, but if you start to look at individual months, like in this case June, and then here in November, you'll see that Northern and Southern California are projected to see quite different rates of change in the future seasonally, and that could be something that's really important to those in agriculture where seasonality makes a big difference. This last tool here I'll show you is looking at extreme heat. So in this case, we look at daily temperature to calculate a historic extreme heat day threshold. So here in Merced, it looks like 102 degrees is a very hot day, but it's not something that hasn't been seen before. And you might expect to cross that around 4 times a year now, but growing up to the 50s and 60s times a year by the end of the century. You could also look at data for minimum temperature and warm nights, also projected to increase quite a bit by the end of the century. And there's just a number of different ways to explore the data. In this case, we're looking at, from April 1st through October 31st, the timing of the days, and you start to see that extreme heat days occur earlier and are projected to occur later in the season than they typically have in the past. This is also really based on location. So what's an extreme heat day in Merced is going to be quite different to Berkeley, where our extreme heat day threshold is 83 degrees, which we're verging on surpassing right here today. So there's a lot of information that can be found in a tool like this, but what we found is that when it's bottled up in our own website, it really limits the use of how people might interact with this information. So we need to make this information accessible to other websites, and we're trying to do this in two different ways. Simply with embeddable maps is easy enough to take that and reproduce it on your website, but even more robust is producing an API which allows people at the original data that we're using to build our own tools so that you can also build your tools around those same data sets. We're doing something like this with biodiversity data here on campus in something called the Berkeley Ecoinformatics engine. And this is a project that we're doing in partnership with the Berkeley Natural History Museums to take lots and lots of ecological data and put it into an API interface that makes it accessible in many different ways for many different kinds of users. So the kinds of information you can find right now in the Eco engine are geolocated specimens. So there are nearly 16 million specimens in the drawers and jars of the museums here, and many of them are being digitized as we speak with geolocation. So all of that information is put up into this engine along with field station records. So as many of you know, there's a vast network of field stations across the state, including agricultural reserves. And many of those have really great wealths of data that have been collected over the last 100 years, and also have climate sensors that are producing millions of measurements in very small increments. We also have really amazing historic data that we're trying to rescue from being lost forever. One of these great data sets is the Wieslander Vegetation Survey that was done by the USGS in the 20s through 40s. And they actually meticulously hand-drew maps of vegetation throughout the state during this time. And colleagues at UC Davis have now digitized thousands of these polygons so that they can be also accessed through this engine and used for analyses, not only to look at what's happening today, but compare it to what things used to look like in the 20s through 30s. While they were drawing those maps, we were also really amazed by the amount of photos they took. Over 3,000 landscape photos were taken during these surveys, and they had the foresight of drawing a point on the map where they took the photo. So we've been able to geolocate all those photos, and now are actually building an application that will invite you to go out and re-find those places today and reshoot them in an example like you see here, where 1940 is on the bottom and 2013 is on the top. This gives our scientists a lot of qualitative information to go along with the quantitative measurements they're doing. So along with all of these kinds of informations we have here on campus, there's many freely available base layers that come from places like USGS on land cover, climate models, and et cetera. And all of these types of information will be available in this same engine. So really the model we're going at here is that we have all this information in a database, many of which have existed in databases, but not kind of a single stop. And all of it will be available through this open API. It currently is. What we're in the process of doing now is building a pretty website around it so that those who are not developers can also access and interface with this data. We'll have different applications that visualize the data in different ways. But because it's open, anyone can build tools around this, and we'll have a gallery of externally developed apps that others have made. For the experts, a lot of the folks here at Cal use R statistics, open source, to do the heavy lifting and analysis of this information. And there's a great project called R OpenSci, and one of our postdocs here, Karthik Ram, developed an EcoEngine package which allows R users to tap into these data resources straight from the R terminal. So you can get at this information from ecoengine.berkeley.edu, and you can build with simple tools like d3.js, really neat, engaging, and active visualizations around data like the sensor data here. And we have an example of that on the website. And soon we'll have that photo resurvey tool where you'll be able to go out and find all those photos that we mentioned and reshoot them today. And that's just a hint of the kind of information available there. And hopefully more will be available soon in this front end we're developing called Holos, which will be the more friendly user interface for all of this information. And really the take home I'm trying to get at here is that we have lots of information and data that allows scientists to do amazing things, And we're really excited to see that science and discovery no longer has to be limited to scientists. And anyone really can now tap into these original data resources and produce engaging interactive outputs for your own. So I'm excited to talk with you all later and learn more about what you're doing in your own projects and how we might be able to assist in that. Thanks.